So let's continue. The next thing that we also need to look into when we're starting working with a lot of data is is another way of storing and organizing the data, and that is through databases. And in principle, a database is a collection of tables containing different kinds of data. Could be just single numbers, but it could also be images that you put into the database. And we already have seen something like it in principle with the pandas data frames, which is kind of a database where you have these tables with some columns in it, and you can do queries. And the idea is that you are not repeating information in the database. So if you have, for example, this, where is it? I lost. Yeah, there is the. Oh, I need to go on again. My pointer doesn't want to work anymore. Okay. No. My pointer is dead. Okay, so then I need to do it this way instead with the normal mouse. So there it is. So we would have then a database of the individuals, and then we do some measurements, and then and with the individuals we have, for example, an ID, a weight, maybe age, etc., etc. And this information we then link to the measurements where we look at, so we see here we have animal 1. That one apparently has some kind of cancer cells, and there is an anisotropy and a volume. And this reduces the table size because now we can only identify the animal and then tell which cells it belongs to, instead of putting all the information that would be very much redundant on several rows in this table. So this is what you do when you work with the databases, that you put relations between different tables. Some are catalogs of individuals, other ones are catalogs of the measurements. And oh, no. It's not meant to be today. So the language that is often used when you work with databases is something called SQL, or I should pronounce SQL. It's the structured query language, and it's used for to search information in the database, but also to add or insert information into the database. And there are different forms of it. So, for example, there is also, let's see, where is the mouse now? There it is. So there are SQLite or MySQL or Hive, different implementations of it, but the language as such is the same. And what it looks like is something like this. A very basic query is select volume from cells. And if you remember the table before, we had, let's see if I can go back. Yeah, so here we had cells, and then I would select the column volume from this cell table. Another one would be to be a little bit do more interesting queries, for example, looking at the average volume from the cell table where the type is selected to be cancer. And then you get an average value for that. So you can actually do already in the query, you can do computations, which makes it easier to work with. And you can do these things also using Excel. You can do it in a pandas data frame if you want. That's of course possible, but the thing is that when you have a database, then the data is stored externally, not in a file that you have to load, but you access the database, which is hosted by some server, and then you can also have larger tables, and you don't have to think about the whole data management because everything is handled by this SQL server. So there are use cases when this is good. In other cases, you may actually go back to using some Panda data frames. And Pandas is good as long as you can keep it in memory of your computer. But there are also, call it derivatives or clones that behave like Pandas, but they can also work towards a file or even have a backend towards a SQL database. And then you can do some more advanced things where you select the volume from cells where the animal is within some range. And then you can get it really crazy where you want to put some, let's see what it's actually doing. We're joining information from different tables about weights and volumes, etc., etc. And then you get, from that you get some index. Now, this is also a thing that you want to use these databases. They are still on a single server, but if you're starting spreading things out on the network, then you could also even get different connections through the networks. And then you need more redundant systems even. And for that, there is something called NoSQL, which is actually not only SQL. And it allows better scalability. So there is this Mongo database system. And then you can also have different specific implementations towards graph analysis, so the graph databases. And yeah, now we come to the big data. And in principle, what we have with big data is the 3 V's, so velocity, volume, and variety. And we need to get to these really fast, so we need some kind of performance system, we need a scalable and flexible system. And yeah, we are ready to handle this when you can handle arbitrary number, also huge number of samples without extra effort on your side, but your computing system needs really to be supporting it. Sometimes you can even be starving for enough data, so there are some that say they even don't have enough data to process. Their system, it's standing idle, and they're waiting for getting the data in. And important thing is also that you have no clicks per sample, because as soon as you need human interaction in your processing, you're lost. Because you can't, if you even would do a single click 1,000 times, that would delay your processing a lot. Because that requires, first of all, that you're sitting there and paying attention to the system. And if you don't, yes?
Can I just quickly ask a question? If we have that much data, we don't look at it ever, how can we avoid errors? We had incidents last week. The student is looking at 2,500 X-ray annotations.
Yeah.
We don't look at the X-rays because we're not allowed these days.
Mm-hmm.
There's just points. And
Okay.
there's
Uh-huh.
is that somehow from 2022 to 2024, the image resolution was higher than before. So
Yeah.
the mode pixel values changed by a factor of 5 to 10, but the calibration line was still the old one. And
Oh.
these alignments were completely distorted. And my question is, how can you double check, or like what I'm now doing is always this kind of redundance checks, backup checks, random patients to check, because the people who extract this data probably made a mistake. But
Yeah.
how do we know if we cannot even look at the X-rays themselves?
If you have blind data, that's a pretty hard task. Yes. Um,
Or do you need to trust the process if you're
you need to have, well, you need to have it sufficiently documented to be able to trust it. But yeah, if it's not documented, that all of a sudden they changed the resolution. That's and or someone didn't get that the resolution was changed.
exactly, because like we figured it out now, but then if the error is not 5 or 10 but 0.01, how do you figure this out?
That's difficult. Yeah. Uh, Thing is, you need the structured and documented workflow as a tool to avoid it, but the human factor is there. It's a hard question, actually. I don't have a recipe answer to it.
So that's something to watch out.
Yeah, so be very strict about documenting what you have, and the difficult thing in your case is it's kind of a blind data because you can't see the originals. That is, yeah, requires quite some thought to make a check for that. Maybe, yeah, a very simple test. No, you don't have the X-rays. I was suggesting like you could look at the image sizes or feature sizes, that you have some kind of sanity check on the features that are detected. Maybe that could help, that you can see in your database, you can see that now the volume or the dimensions of things changed in a strange way, having some kind of indicator on that. Now I don't know exactly what information you exactly have, but maybe you can do some histogramming, like the pair plot, seeing if the pair plot just has a single blob or say a natural blob, or if there is all of a sudden a deviation in this blob. And then you can do it maybe from year to year or the whole data set, and then you can do comparisons as some kind of cross-check. But yeah, if you don't have the image data, and just get tables, that's not easy. Yeah. Yeah. And now that you want to look at this big data, Google is known for handling a lot of data, and they want to do something called PageRank, so evaluating the quality of the websites. And that algorithm as such is looking for each image, each website, and call this PageRank for that site, and that for every site on internet. And well, that is quite a huge problem. So the question is how to split it down and do it efficiently. And one way is to call this PageRank algorithm, where you do the analysis, and then for every other site, compare this if there are links to this other site, and add those links to that one. And the whole search procedure here ends up in the complexity order n², which means this will blow up and take months to compute. Even on the most powerful computer, you will not be able to do it. So you need to do some kind of smart rearrangement. And Then, of course, you have the additional problem that if you have this huge computing resources, you need to be safe against computer crashes, hard drives, etc. So you need also a lot of redundancy and backups. But it's a lot of computers, so you can't really have a backup for each one of them. And maybe even an earthquake crashes a whole computer site. And adding to that, PageRank doesn't just count, but it also keeps track of old rankings for the page. And it means it needs to run this algorithm several times to converge. So it's a really complex system that they're looking into. And for that, they invented something called MapReduce, which in principle you have two basic operations. You have mapping, where you you have an input vector and then you map it or apply a function on it. In this case, the mapping is the x squared. And the result of the mapping is then the squared vector here. Then you have reduction, which reduces the contents of this vector. And in this case, we have the reduction a plus b. And you want to compute the sum of the vector. And it's a very basic, so it takes two operands. And if you call the reduce, you can iteratively call it. So first you do the sum of 1 and 2, and you do the sum of the result with the 3 and 4, and so on. So you iteratively call through this mapping reduction part. So what you can do in that case is, first of all, you partition your whole input data into chunks on the machines in the clusters. Then you do some mapping and do shuffle and repartitioning or group the data. Then you can apply the reduce on each of these groups and then collect all of the results and write it to disk. So in principle, a task is then you have a data vector, you have a mapping, and you have a reduction. And that is called then a job. And often it's about key value pairs or grouping, where we have to map all these parts together. And usually we have then a value associated information to every key. And the keys, they are actually the sorting component that the computer is working with. To bring it away from the more abstract things, we can use it to count words. So if we have a sequence of sentences, then that is our vector, and then we do the mapping. And the mapping is that each word gets just a 1, and we split that to on every space. So then we get instead a vector of word, comma 1, next word, comma 1, etc., etc. And then afterwards we group all these keys. So every word that has the same, every entry that is the same will be grouped together as you have one, and then you will have a vector of several ones, and those are reduced afterwards. So to put the example here, we have the two sentences. We have cat, dog, car, dog. And when we do the mapping, you get cat, comma 1, dog, comma 1, and so on. Then we do the shuffle and grouping. We can see there is only one cat. The dog got 3 ones, and the car got 2 ones. And finally, we do the reduction. So we just sum how many there are of each, and then we have the word count. This looks maybe a bit overcomplicated, but it's a more efficient way in the algorithms that these systems are using. So we can do a word count example. We can take the Shakespeare Midsummer Night's Dream. So we open up we open it, we get all lines, and if we print it, we get this text here as our L vector. Then by doing some collections, there's a lot of code here, but mainly we do the stripping and we do some reshuffling here, and when this is called, actually that one, nah, I wouldn't challenge doing this now. But afterwards we got this word count items, and we can sort them for the most frequent ones, and we can sort them for the least frequent ones. And the most frequent ones are quite obvious. The least frequent ones, they are quite strange words. Some I think I never heard. And they only got 1 count, each one of them. And another thing here, we have also an MapReduce approach. And often when you want to do this kind of programming, it is good to have the built-in doc test function. So here we have an auto test that checks that it's doing the right thing. So every time we execute this part, it's, oh, that wasn't meant to be. Okay, it worked yesterday. Probably I didn't initialize something on the top, so that's why I got this exception. So one thing that we can work with is a toolbox called Dask Bags that can actually implement operations like mapping, filtering, folding, and grouping. And the idea with these bags is they can actually perform tasks in parallel, and you can even do it iteratively. And when you have defined these bags, you can also do lazy operations. You more or less define the steps, and then at some point you call it to execute, and then you get good execution, even for larger than memory data on a single machine. So to do this, we I didn't load the Shakespeare data now. Yeah. So in principle, you just say here, you get a bag of the of this Shakespeare text with some partition size, and then you can see here what it is. And it tells us that we have 13 partitions that will be executed as subtasks in the parallel execution. Then we do some flattening and see what happens. It's still 13 partitions. And then we can do the reduce output. So then we have this output we call the frequencies, which in principle is a histogramming function. And then we can look at the top 10 examples. So this would be the most frequent ones, and top k in this case is the least frequent ones, because the search operation here is taking it from the back of the table. And then we can run, and we get actually the same kind of result as before. So we get again the and I, etc. with high counts, and we get the other ones here going down to the filched, which only has 1 count each. So, and that can also be visualized nicely. We can look at some visualization where you can see how the different workers are running, also how the memory is used and the CPU is used. This was a bit too big printed now. So that was one example how you can split and divide data into smaller chunks and send it out on parallel processing. There are also some environments for distributed computing. So there are Hadoop, some an alternative to the MapReduce, which is open source. And many of the big ones are actually using it to deal with a lot of data in their processing. And then we have Spark, which is another kind, and we also have practical distributed system where you don't have to think much of all this logistics and libraries and compiling, and it's usually working declarative rather than imperative. So we don't want to, and so what we usually do is apply the same operation on each image block, and not tell computer 3 to wait for computer 2 to do something, because that's usually on the image data is not so efficient. Scheduling can be handled automatically here. Or it can be also, and the results can be stored where you want it, and you can even tell if it's redundant or not. So, Dask is a framework that works nicely in the Python system. It aims to bring you fault-tolerant processing and also robust distributed computing, and that on Python code. And the thing with Dask is that it actually has implemented many of these usual libraries that we have been working with until now, like NumPy and SciPy. They are already implemented in Dask, so you have the same syntax as you have in NumPy and SciPy. With Dask, you just change the first name. Instead of writing NP, for example, for NumPy, you write Dask and some extension. And yeah, these are used also in Spark. The DAGs is a more general implementation than these MapReduce, and that is actually used in many of these packages and allows also massively parallel computing in a nice and declarative way. So here are some resources to where you can find these different DAGs. But now, okay, there is an example. Execution is something that takes time, and if you have very many computations of the same kind, you want to distribute it on many tasks, then it's important to find the most important, the fastest implementation. And there are some code generation examples, how the averaging in some CUDA code, so that is for the graphic card, how that can be regenerated in different ways to execute the code most efficiently. And this is an example how Facebook have done some optimizations on their code. So here is, now we switch on to the DAGs and how they happen, what's going on. And so let's start here with the Dask array, which is the same as the NumPy array. And then we just have something for visualization. So here we create image 1 is just zeros, 5 by 5, and we say it's in 5 by 5 chunks. We have image 2, which are also, it's only once in a 5 by 5 image, and then we want to look at it, and it looks like this. So we have this variable, and here is the mapping to the blocks. Oops, sorry. And let's see, that one should run. Yes, it does. And if we want to do some arithmetics, we can do, we have here image 1 minus 10 plus image 2 times 50. And that can be outlined like a graph, like this. We can see the operations that are executed, and afterwards finally the add is taking place. So it actually breaks down your computation into a tree of execution pieces. Then we can do even more computations. You can see here there are some linkages. So we have image 5 and image 4. So this piece here is the image 4, and this is what is needed to bring in image 5. So this is just a single operation, and actually what you write is this piece here. You don't have to actually see this graph, but it's just to see what is going on. Let's try this on now some bubble data. And here we load. No, come on. Yes, there it is. Okay, so this is what the data looks like. We have, this is just a sum of all frames through a bubble sample, and here we have 10 frames extracted from that data set. Now let's create a DAG from this foam image. The image is 100 by 400 by 400, and we want to create 20 slices per chunk, and the scale intensities should be scaled from 0 to 255 to the range 0 to 1. So we create here our task array from a NumPy array, which is this one, and we divide it by 255.0. And we say that the chunks should be 20, 400, 400. And it should be called foam image. So this is what is represented. We have now 5 chunks out of this data, and we want to run it. And now we want to add a filter operation on this. And one way of doing it is just to do map blocks and put the Gaussian filter from SciPy with some filtering weights. And that results in this kind of representation. The problem here is that these will be individually filtered blocks, and that means all the boundary processing will be repeated between these blocks. So this is not the ideal way of doing Gaussian filtering in Dask. So what we need to do instead is to do map overlap, and the code looks all of a sudden quite much more complicated when we look at it. And there is this extra overlap and get item pieces, even more overlap, and it looks very complicated, the whole thing. And the reason for this, oops, no. The reason for this is now the code has a little bit overlap between the different sub-blocks to be able to handle the edge processing of the filters. And with that, we have a correct filtering of the data. And now we want to erode, so we want to apply a threshold at 0.9, and we want to erode with the bulk structure element radius 12. And again, we do the map overlap, and this looks like a messy forest. But in principle, what it does is first, so we take this original image that was filtered and add on to the processing. We add on now the erosion task. So when we look at this, we can actually recognize the first piece here going to here is the filtering that we defined before. And the second part is applying the threshold and the binary erosion. and that is also again with some overlapping. And then we can also finally add even the labeling of these blocks, and then we do block label, some code here which is also again from SciPy and the image, and that results into some execution that I'm not going to run now. And unfortunately, I must admit, I didn't get it to run because yesterday when I tried to test this code, I realized that Dask has changed its API, and the things I had before, they were deprecated. So I had to redo a lot of things, and I wasn't able to finish up the final execution. So, but we have at least we have these summed slices. What I missed doing was filling up the gaps, because this should be full, and I didn't get the labeling right, so I need to look at that afterwards. And when you execute these, it's very important that you think about the operation order, because depending on how you operate, you can take more or less time. So one is, if you want to select, you want to have a single filter slice, what you can do is select a slice and filter it, or else you can also do the filtering and then from the result select a slice. And this one, of course, will turn into a lot of more processing, because you have to filter the whole image before you can extract this slice. And when running this, we can see that it takes longer time to do filtering the whole thing than doing the filtering of a single slice. There is overhead in the processing, which makes it, the gain is not so big in this case. And I also don't have that many workers running here. Yeah, and the difference is actually that the first selecting a slice and filter only approaches a single block of these of this graph, and if I want to filter and select a slice, I need to actually use all the blocks at the same time. So that is where you spend more time. And then we have a little bit about cloud computing. The idea with cloud computing is that we have a lot of, so computing is expensive, and it requires maintenance, it requires investment, and often it's not worth buying your own big computer, because you can actually buy these resources. And in the cloud services, you have, to some degree, you have free computing hours, but then you can also select more powerful computers, or you can apply for computing time on big systems. And then you can use only the piece when you need it, and only pay for the part that you need. And they have usually set up the whole infrastructure that you would need for your processing. Or you can upload your own code, of course, too. And yeah, and then there is a lot of platforms for it, and they have usually they have a lot of available tools built in already, and they are already optimized for the use. And yeah, then of course you can also have some of them, they are available on GitHub, and you can reduce the amount of code in comparison to that. And I think this one, that's actually an old comment. But there are a lot of courses which are based on these systems. So you can actually easily have them available and learn more about them if you like. Another thing is streaming. Sometimes when you do your experiments, the data is actually produced on the fly, and you need to process on the fly too, and that is a big challenge because the data there is so much data produced that you don't have a chance of even keeping it all. So you need to process it on the fly. So that is a challenge here. So we need to add maybe scalability. So we need maybe to connect more computers and start workers to be able to handle this streaming task. And and then we have, that's just the database. Also, sometimes when you have these big databases, you're not able to handle the amount of data in the time given. So you say, compute the mean as good as you can within 5 seconds, or with maybe compute it to reach a confidence interval of 0.95. Something like that. You can put restrictions on the computations to meet your deadlines in time, and that's for the really big systems. I think most of us probably don't need this, but sometimes it could be relevant. Yeah, and that brings us to the end of today. I actually also have a little summary, just a little wrap-up of what we have been doing this spring. So this is more or less just a summary now. So why QBI? So we have a lot of experimental data. We have limited time and usually also limited manpower. And of course, we want to publish the results of the data in a quantitative manner. And that should also be reliable and repeatable. And for doing this, we also want efficient automated workflows to meet the results of this. So we have parts that we need to understand is first the data creation, also some image processing and analysis methods, how to work with the data, some computer science engineering needed, and also how to present the results in a good way. And our workflow is, in principle, that we... Nah, that's not working, still not. Now it came up. It's alive. So we have first a little bit general about images, using data sets, and then we did some filtering, segmentation, and more advanced segmentation, shape analysis, some classification, statistics. Then we came into some more specific types of experiments that require extra thinking, time series, and multimodalities. And today we talked about the computational resources needed for taking care of all this data that we produce. Then I'm just going through here. Lecture 1 was about the image basics, what's an image, pixel operations, histogram. Then we looked at data sets and validation, how to work with prepared data sets, and also a little bit about analysis and validation workflow, and the usefulness of the ground truth. Image enhancement. In every measurement we have noise, and here is much about reducing the noise, but also about enhancing different image features. And we also looked into filter performance analysis, how different filters perform compared to each other. And the basic segmentation, how our image is formed, what is a change in contrast meaning, and also how to apply different thresholds. The thresholds turned more advanced when we found methods to apply find these thresholds automatically with supervised and unsupervised methods. Then we looked into component labeling and shape properties and a little bit about textures. Then we looked into the complex shape, where we were looking into the labeling of touching objects and also on skeletons, the minimal structure that's spanning up the objects. Then statistics, unfortunately a lecture that I couldn't be here to tell you, but you got it recorded. So probability, implications of the statistical analysis, presenting the results, and here I actually forgot to add the uncertainty, which was also the first part of that lecture. Dynamic experiments, time series, and what challenges comes up. And multimodality, using more than one modality to do the imaging, and what kind of fusion you can do with that data. Another part was software engineering, how to work with your code, testing it, working with repositories. And today we talked about the parallel processing, distributed computing, and the DAGs. Finally, we have the project. Some of you are doing it, some not, but the idea is that on Thursday in 2 weeks we're going to present the results, and the idea behind this project is to get a little bit feeling of a larger project where you can see how you can put in the different things you have learned during the lectures. And I encourage all of you to come to see the presentations, not only those who did the project, because you may see and learn things from what other people have done, and also see more practical examples from this work. And yeah, project support per email. I didn't update that one. I see. Okay, that was from last year. But anyway, next week there is no lecture, but we are available for your support. I would say make an appointment during the week, and we probably discuss it over Zoom or email, however you like. So I'm not going to be in Zurich next week, but if you want, we can always do an appointment, and the same goes actually for the week after. Then you can also just make an appointment if you get stuck on something. And that was the end.